Hi everybody, it's Professor Mitchell. Today we're starting chapter 7 on decimals, percents, and real numbers. In this first section, Terminating Decimals, we'll talk about decimal notation, connections between fractions and decimals using various models and strategies, why terminating decimals occur, and how to tell if a decimal will terminate, and finally, ordering of terminating decimals. The word decimal comes from the Latin decim, meaning 10. The decimal number system has as its base the number 10. We can represent this decimal number as follows: 1 times 10 plus 2 times 1. Notice that 1 is in the tens place, 2 is in the ones place. And then after the decimal point, we go 6 tenths plus 1 100th plus 8 thousandths plus 4 10,000ths plus 3 100,000ths. And this decimal number is read 12 and 61,873 hundred-thousandths. Each place of a decimal may be named by its power of 10. So we already know about hundreds, tens, and ones. The numbers after the decimal point, those place values are tenths, hundredths, thousandths, 10,000ths, and so on. Suppose that a long in the base 10 block set represents 1 unit instead of letting the cube represent 1 unit. Then the cube represents 1/10. So earlier when we were dealing with whole numbers, these longs represented tens. So now, and the little cubes represented ones. So now we can let the longs represent ones and the little cubes represent tenths. So in this model here, we're representing the number 5 and 4/10. To represent a decimal such as 2 and 235 thousandths, we can think of a block as a unit. So we have 2 blocks, 2 flats representing 2/10ths, 3 longs representing 3 hundredths, and 5 cubes representing 5 thousandths. In this example, we'll convert each of the following to decimals, starting with 25 tenths. So what we want to do with that first is basically change it to a mixed number. And they're doing that the long way. We talked about the shortcut a few sections ago. 25 tenths is 2 and 5/10, which as a decimal is 2 and 5/10. It's written like that. These other ones are a little simpler because they are proper fractions. 56 hundredths is written 56 hundredths. 205 10,000ths is written like this. Notice the 0 between the decimal point and the 2. That's very important. If that wasn't there, then that decimal would be 205 thousandths. All right, continuing, we have 7 over 2 to the 6th. So what you want to do in a problem like this is we want this denominator to be a power of 10. So to make it a power of 10, we'll multiply the top and the bottom by 5 to the 6th to go along with our 2 to the 6th. And what that will do is it will allow us to write this 2 to the 6th times 5 to the 6th as 10 to the 6th using this property of exponents. And what we end up with is 109,375 millionths. 10 to the 6th is equal to 1 million. All right, next we have 1 over 2 to the 3rd times 5 to the 4th. So again, we need the power of 2 and the power of 5 to be the same. So in order to bump up this power of 2 by 1, we will multiply the top and the bottom by 2 to the 1st. So that will give us 2 over 2 to the 4th times 5 to the 4th, which is 2 over 10 to the 4th, which is 2 10,000ths. All right, this would be a great time to pause the video and try these two yourself. So now we're going to start by prime factoring 125. Its prime factorization is 5 to the third. So we need a 2 to the third to go along with that 5 to the third. So we'll multiply the top and the bottom by 2 to the third. That gives us 2 to the third over the third power of 5 times 2, which is 10 to the third. So we end up with 8 thousandths. And finally, 7 over 250. 250 factors into 2 times 5 to the third. We need this power of 2 to be 2 to the third, so we'll multiply the top and the bottom by 2 squared. That's going to make this 2 cubed times 5 cubed, which is 10 cubed. So we end up with 28 over 10 cubed, which is 28 thousandths. So what we get out of those 4 examples is that these decimals will terminate. Well, let's back up for just a second. Decimals that can be written with only a finite number of places to the right of the decimal point are called terminating decimals. And now what we saw in those previous examples is that the denominator of the fraction needs to be written with powers of 2 and powers of 5. So a rational number, a over b, in simplest form, can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 or 5. This is the only math class I know of where that comes up, so that's kind of a neat fact. Here are some examples of rational numbers that can and cannot be written as terminating decimals. 7/16, 19/40, and 3 over 160 can all be written as terminating decimals because their denominators can be written using only powers of 2 and 5. However, 11/18, 5 over 26, and 9 over 84 cannot be written as terminating decimals because the denominators contain prime factors other than 2 and 5. Now this one here bothers me just a little bit because that fraction is actually not in simplest form, right? You can take a factor 3 out of that. So do be careful and make sure your fractions are simplified first. I have a feeling they didn't mean to do that. If you were to simplify this fraction, you could take out a factor 3, and that would leave you with 3 over 28, but you would still have this prime factor 7 in the denominator. So this would not be able to be written as a terminating decimal. Ordering terminating decimals. Terminating decimals are easily located on a number line because they can be represented as a rational number a over b, where b is not equal to 0, and b is a power of 10. So for example, the number 56 hundredths can be found by dividing the interval between 0 and 1 into hundredths, and then just counting 56 hundredths of the way over, all right? If you were to actually do this, those little intervals would probably be much, much smaller than this. Notice they skipped a bunch of them, all right? But it can, at least theoretically, be easily done. Okay, notice that 56 hundredths is between 5/10 and 6/10, because 5/10 is 50 hundredths and 6/10 is 60 hundredths. All right, so to close out this section, we will compare these two decimals, 67,643 hundred thousandths and 6,759 ten thousandths. So the easiest way to do that is to just line them up by their place value, and then start at the left and find the first place where the digits are different. So that occurs in the thousandths place. So comparing these digits, the number containing the greater digit in this place is the greater of the two numbers. The digits in the thousandths place are different, and 6 is greater than 5. Therefore, 67,643 hundred thousandths is greater than 6,759 ten thousandths. And that's going to do it for this section. We'll see you next time.